Welcome to the deep dive. Today we are pulling back the curtain on some knowledge that really underpins infrastructure safety all over the world.
Mm.
We're looking at a set of official safety protocols for system testing and commissioning, and our source material actually comes from a major electromechanical project group in North India.
Right.
And this isn't just about, ticking boxes for compliance. This is the tactical playbook that engineers, highly trained engineers, rely on to manage some really extreme risks.
It's the operational synthesis, really. When you look at these documents, you see they connect four huge fields of risk.
Okay.
You've got high voltage electricity, you've got extreme pressurized systems, hazardous chemicals, and then just the inherent dangers of construction work itself.
Like working at height-confined spaces.
Exactly. So for any project manager or a safety officer or commissioning engineer, this stuff is basically a universal roadmap, the distillation of decades of hard-won lessons in industrial safety.
And that's our mission for you today. The goal is to extract the most critical, the most high-consequence procedures from this.
Essentials.
The essentials, yeah. We need to identify those foundational safety steps that are they're non-negotiable. And then we're going to zero in on the unique and often kind of invisible hazards that come with commissioning complex systems like HVAC and firefighting.
Sounds good.
Okay, let's unpack this. So the first segment, let's talk about what the sources call the non-negotiable general protocols.
Right.
These are the rules that apply no matter what you're doing, whether you're installing some ductwork or, testing a massive fire pump. And the first line of defense is always going to be PPE.
Personal protective equipment.
Yeah.
And the baseline is very clear in these documents.
Mhm.
Hard hats, safety glasses, high visibility vests, gloves, and steel-toed boots.
Yeah.
That's the mandatory minimum just to be on the site.
Just to walk through the door.
Right. But the real complexity,
Mhm.
and where the protocols get interesting, is when the specialized hazards show up.
Exactly. The protocol demands this kind of dynamic PPE selection. So, for instance, if you're doing voltage testing, your standard work gloves are useless.
Completely. You need specialized, insulated electrical gloves.
Yeah.
And rubber mats, too, to protect against what's called step potential.
And what if you're dealing with chemicals, say opening a cooling tower or using certain sealants?
Then the requirement immediately shifts. You're looking at respirators, maybe even chemical-resistant suits. It's an immediate, task-dependent assessment you have to make.
So if PPE is there to manage the consequence of an accident,
Right.
lockout to gout, or LOTO, is what prevents the accident from ever happening in the first place. It's all about controlling hazardous energy.
It's the absolute gold standard. The protocol defines LOTO as this comprehensive process of de-energizing and securing equipment before you even think about starting any testing or maintenance.
Now, LOTO sounds straightforward on paper. Flip a switch, attach a lock. But in a really complex electromechanical environment, how complex is it to actually achieve that zero energy state?
That is a great question.
I mean, can you ever take shortcuts if the main power source is, say, kilometers away?
And the answer is a hard no. No shortcuts. In fact, LOTO is where these procedures get the most complex. The documents insist on a total verification of a zero energy state.
So not just electricity.
Not just electricity. You have to deal with stored energy. Think about pressurized fluids in hydraulic lines or compressed air.
Trapped mechanical energy, like a spring under tension.
Exactly. Or even electrical charge that's still held in capacitors. Every single one of those energy sources has to be isolated and physically discharged.
So you're talking about multiple isolation points, multiple checks, and this is probably spanning across different teams, right?
Oh, absolutely.
I can imagine coordinating OTO on a big air handling unit, an AHU, where you have one team on the electrical panel, another team managing a pressurized line, and a third testing the motor. That must get incredibly intricate.
That's where group LOTO procedures come in. And the complexity, as you said, it just escalates dramatically.
So how does that work?
The protocol details a system where a central authority issues a master lock to a supervisor. That supervisor applies their lock to the main isolation point.
Okay.
Then individual team members, they attach their personal locks to a lockbox or some kind of group isolation device.
Ah, I see.
And no one can remove that master lock until every single person working on that system has come back and removed their own personal lock. It guarantees safety for the whole crew.
It turns energy control into a bureaucratic process, but
A life-saving one.
a life-saving one. Okay, so moving from energy control, the protocols also talk about controlling the environment and communication. This brings us to hazard communication, or HAZCOM.
Right. HAZCOM is basically the requirement to know the chemical fingerprint of your worksite.
The chemical fingerprint, I like that.
You need to understand the safety data sheets, the SDS for everything on site, cleaning agents, sealants, lubricants, and critically refrigerants.
And it's not enough just to know,
Yeah.
right?
No, knowledge isn't enough. The protocol demands really stringent procedures, proper labeling, dedicated storage areas for things that are flammable or toxic, and documented disposal methods. You can't just, toss an empty can in the general trash.
And while HAZCOM deals with the chemical environment, the protocols are also extremely strict about the physical environment, especially confined spaces. What defines a confined space in this context?
It's any space that's large enough for a worker to get into and do their job, but it has limited or restricted entry and exit. And crucially, it's not designed for continuous human occupancy.
So we're talking about big air ducts, storage tanks, pits.
Exactly. And the defining factor is risk. Before anyone goes in, the protocol demands a formal permit system.
And what does that permit involve?
It means you have to do atmospheric monitoring, checking oxygen levels, flammable gases, toxic vapors, and you have to have a pre-planned, immediately deployable rescue team on standby.
So you can't go in until you know what's in the air, and you know exactly how you'll get out if something goes wrong.
You got it.
It seems like these protocols are really structured to mitigate those high-consequence, low-frequency events. But we can't forget the simple stuff.
No.
The source material actually spends a good amount of time emphasizing good housekeeping. Why is cleaning up debris considered a critical safety protocol when we're talking about high voltage and high pressure risks?
Because statistically, the most frequent incidents on any site are slips, trips, and falls.
The simple stuff.
The simple stuff. A cable left across a walkway, a piece of sheet metal leaning where it shouldn't be. These seemingly small failures in housekeeping lead to a ton of injuries. They tie up medical resources, and they delay the entire project. The protocol treats a messy site as a failure of immediate risk assessment.
Okay, let's pivot from those foundational rules. When we transition into commissioning HVAC systems, we're introducing a whole new layer of very specific risks. It's a combination of electricity, pressure, and unique chemistry.
That's right. The HVAC commissioning process is inherently dangerous because, for testing, the system has to be functional.
It has to be on.
It has to be on. Components have to be temporarily energized or pressurized. So while a low dose still applies, the protocol requires extreme precision in electrical testing.
Meaning what?
Meaning every piece of equipment you use to check voltage, your meters, leads, probes, it all has to be rated and insulated for the expected voltage. You simply cannot use uninsulated tools. It's an absolute rule.
This is where the hazards become really insidious refrigerant safety. For most people, refrigerants are just the stuff that makes the air cold.
Right.
But the protocol treats them as high-stakes chemical hazards. What are the primary dangers that the source material really emphasizes here?
It lists 3 critical hazards. First is asphyxiation.
Okay.
A lot of modern refrigerants, like R410A, are heavier than air. So if a line ruptures in, say, a basement equipment room, that vapor just pools at floor level and it displaces the oxygen.
So someone walking in could lose consciousness almost immediately.
Immediately. The second hazard is frostbite and chemical burns. When refrigerants change from liquid to gas really fast, which is what happens in a leak, they become intensely cold. Direct skin contact will cause a severe cryogenic burn.
That rapid transition is just a massive energy release. And I imagine the protocols for handling these refrigerants must be incredibly tight, especially now with the global phase-out of older gases like R22.
They are. The protocols demand that handling, charging, recovery, all of it has to strictly comply with national and international environmental regulations.
So it's not just safety, it's legal compliance.
It's both. It means only certified technicians using purpose-built refrigerant recovery equipment. It means storing cylinders upright, secured in well-ventilated areas away from any heat source. Any failure here is both a safety hazard and a big environmental liability.
And moving beyond the chemicals, HVAC is a system of high pressure.
It is.
So this includes safety during pressure testing of coils and lines, which is often done with dry nitrogen to find leaks.
You're dealing with a massive amount of kinetic energy stored in those lines. The protocol demands that pressure testing is done in controlled, incremental steps.
Slowly.
Very slowly, and only after you've secured the lines and coils against any movement. But even before that, you have the hazard of the compressed gas cylinders themselves.
The nitrogen tanks.
The oxygen cylinders, yeah. They're stored under thousands of PSI. If a valve on one of those gets damaged or knocked off, that cylinder becomes an unguided missile.
Wow.
So secure storage, robust capping, chaining them during use all absolutely non-negotiable protocols.
I can visualize the chemical and pressure risks, but what about the physical structures? The source material even highlights dangers like sharp edges on ductwork.
It sounds minor, but sheet metal is unforgiving. Cuts from improperly finished duct edges are really common. So the protocol demands that edges are handled properly and that cut-resistant gloves are always used.
Right.
And more critically, there are detailed safety protocols for lifting and moving heavy components.
Compressors, condenser unit.
Big motors, yeah. We're talking mechanical lifting plans, certified slings, and clear communication to prevent crush injuries. It's another high-consequence failure point.
And finally, for HVAC, the invisible risk of air quality. Even when the system is supposedly finished, the environment can still be toxic.
Absolutely. Think about old ductwork being replaced or cleaned or working in areas where construction dust and mold have accumulated. The protocol requires respiratory protection, not just a dust mask, but a properly fitted respirator if the air quality is compromised.
And that's to protect the crew long term.
Long term, from things like silica dust or pathogenic mold spores that can thrive in damp mechanical spaces.
Okay, now we shift gears completely. We're moving from the air and chemicals of HVAC to the sheer relentless force of water under pressure, firefighting systems.
Right.
Testing these systems involves massive flows, high pressure, which means any procedural failure has immediate catastrophic consequences, often involving flooding.
And the centerpiece here is what's called hydrostatic testing. This is the procedure for proving the integrity of the piping network.
How?
By pressurizing it, usually with water, far beyond its normal working pressure. It's essentially an induced stress test.
So detail the protocol for us. How do the sources manage a scenario where a pipe or a valve could literally explode under that enormous pressure?
The preparation is almost surgical. First, safe isolation. The section you're testing has to be completely isolated from the main system.
Okay.
Second, the filling procedures are deliberate. You have to remove all the air pockets. Then the application of pressure must be gradual and controlled, monitored constantly by people watching from a safe distance, a pre-established exclusion zone.
Because if a pipe ruptures under a hydro test, it's not a leak.
It's an explosion of water and shrapnel.
That need for control brings up a point about the equipment itself. If the whole test relies on an accurate pressure reading, the testing devices must be infallible.
Precisely. The protocol explicitly requires the use of certified pressure gauges and certified test pumps. You can't use a cheap or uncalibrated gauge. The certification ensures accuracy, which is a life safety issue.
And the risk isn't just component failure, it's also water management. It's the danger of creating a local flood.
Yes, and that requires strict logistical steps before any test begins. This involves what's called an impairment procedure.
Can you elaborate on that? What is an impairment procedure?
It's the formal process for taking a life safety system offline. It's a cascading safety action. Before you isolate anything, the protocol demands that building occupants are formally notified.
Right.
You have to establish a fire watch, a dedicated person or team ready to manually respond to a fire. And you implement controls like locking out the system's alarm panels so they don't cause a panic during the test. All of that is required before the water is even turned off.
That level of detail really shows how interconnected mechanical safety is with occupant safety.
They are one and the same in this case.
So the procedures for controlling the water flow during functional tests must also be complex.
They are, particularly during fire pump testing. When you test a high-volume fire pump, you're removing thousands of gallons of water per minute. The protocol demands clear starting and shutting down sequences and constant monitoring for irregularities.
Vibrations, strange noises.
Overheating, anything that signals impending mechanical failure.
And what about managing that massive water discharge during a flow test? You can't just open a valve and flood the parking lot.
No, the protocol stressed that managing that discharge is a major hazard in itself. You have to use dedicated diffusers or temporary piping to direct the water away from people, away from electrical equipment, foundations, adjacent property.
Uncontrolled discharge could cause real damage.
It can erode soil, flood basements, or turn a walkway into a serious water hazard.
And that combination of high-volume water and electricity, that has to be the ultimate hazard.
It creates a dual-threat environment. First, the slip and trip hazards are dramatically heightened. Water on concrete is treacherous.
And
Second, and far more dangerous, is the electrical hazard. The protocols explicitly forbid using any non-waterproofed equipment near the water flow. And they require stringent inspection of all junction boxes and power sources to ensure they're sealed and protected. A simple short circuit in a wet environment can lead to immediate electrocution.
And finally, we come back to inspection. The necessity of thoroughly checking components like sprinkler heads and valves for damage or obstruction.
This is the final layer of defense. You're inspecting for corrosion, verifying that sprinkler heads have the correct temperature rating, ensuring control valves are lubricated and fully operational.
And you have to operate those valves safely.
Crucially, it means using the right tools, checking seals, and confirming that the valves, which are critical for isolating the water, are properly supervised after the test.
What does supervised mean?
Usually it means they are locked or chained in the correct position, either open or closed, to prevent anyone from accidentally or deliberately tampering with them.
So what does this all mean for you, the listener? We've traced a path through 3 pretty complex areas here.
We have.
First, controlling every form of hazardous energy through procedures like Group L LOTO. Then, managing the invisible threats of chemistry and pressure in the HVAC domain. And finally, mitigating the high-consequence environmental risks of massive water flow and electricity and fire systems.
And understanding these layered protocols is really the essential shortcut to assessing competence and risk on any major project. You've basically turned what was a high-volume compliance binder into actionable knowledge.
Right. Knowledge about where the highest stakes failures truly lie in mechanical commissioning.
And it informs everything: planning, budgeting for safety equipment, assessing the training level of your crew.
And we found a fascinating signal in the source material itself. The engineers who wrote these protocols, they specifically asked if elaboration was needed on only 2 procedures: lockout, tagout, and hydrostatic pressure testing.
That's right.
And that tells us exactly where the project team believes the consequence for error is most catastrophic, most unforgiving.
Which brings us to our final thought. While these protocols stress human vigilance and procedural adherence and all these precise steps, the entire system relies utterly on the integrity of external infrastructure.
What do you mean by that?
I mean, certified pressure gauges, certified recovery equipment, certified locks, certified test pumps. In high-stakes testing, the outcome doesn't just rest on the engineer's hands, but on the certified accuracy of the tools they hold.
So our question for you is this. What does that necessary reliance on certified infrastructure tell you about the hidden architecture of safety that must be built before any human action can even begin?